With a caliper and a micrometer, we read the size of a part. With an indicator, most of the time we do not read size, but deviation. In other words, we quickly see how much the part shifts from a reference value. That is why it is one of the most practical tools in the shop for runout checks, alignment, level differences, and parallelism. In manufacturing, the need was simple: make very small movements large enough that everyone could read them the same way. This idea matured with amplification mechanisms similar to clockwork. Over time, two main families appeared: the type with a tip that moves in and out in a straight line, and the lever type. Where higher sensitivity was required, the same approach continued with electrical measuring probes. Now to the core question: what is an indicator? An indicator performs comparative measurement. Rather than giving an absolute number, it shows the difference relative to a reference value. That is why the first step is always the same: choose your reference, then define your zero. Zero does not have to be the true size of the part. It can simply be your starting point. With that clear, let's quickly identify the main parts of an indicator. On a linear type you have the body, the mounting stem, the contact tip, the dial, the pointer, and the zero setting bezel. On a lever type the contact tip is connected to a lever. The dial and pointer are still there, but the contact angle becomes more critical. On digital types you see the value on a display, and you can set the starting point quickly with the zero button. So how does an indicator work? On a linear type, the contact tip moves in and out. Inside, this motion is amplified by gears and transferred to the pointer. Two things matter here: the resolution and the measuring range. The logic is the same on digital types as well. You see the deviation as a number on the screen. The lever type is especially practical in hard-to-reach areas, when scanning a surface, and during alignment. The key rule to remember is this: the more the contact direction differs from the direction you want to measure, the smaller the value you read. So keep the tip working as close as possible to the direction you actually want to measure. Also, if the contact point is not positioned correctly, the body can rub instead of the tip, and that will distort the reading. Up to this point we covered what the tool does and how it behaves. Now let's address the same part, same tool, different result issue. An indicator is not a complete measuring system by itself. The stand, the mounting elements, and the contact setup are part of the result. If the stand is loose, joints are moving, or the magnetic base is not seated properly, you are not reading the part, you are reading the stand's deflection. That is why it helps to think of the use in 3 steps. 1. Mount it solidly. Seat the base on a clean surface, tighten the joints, and apply light pressure at the tip. 2. Zero to a reference. That reference can be a gauge block, a ring gauge, or a known good part. 3. Move in a controlled way in the direction you want to check, and observe the maximum and minimum values. Now let's connect this to the most common application: runout checking. While rotating the part, the difference between the highest and the lowest reading gives the runout magnitude. Here, keeping the measurement point and the contact angle consistent is essential for repeatability. If the measurement point shifts, the reading shifts as well. Now let's summarize the main errors that distort the result. 1. Wrong contact. If the body rubs the surface instead of the tip, the reading becomes unreliable. 2. Angle error. As the contact direction moves away from the measurement direction, you will make the deviation look smaller than it really is. 3. Backlash and friction effects. If your approach direction changes, the reading can change too, so measuring by approaching as consistently as possible is a good habit. 4. Choosing the wrong sensitivity. If the acceptance band is tight, a coarse resolution is not enough. If you go too sensitive, you can unnecessarily complicate the setup and increase the effect of vibration and pointer fluctuation. In practice, there is also a useful way to read with an acceptance band. Bring the part to 0, then mark the upper and lower limits in your mind on the dial. As long as the pointer stays within that band, the part is acceptable. If it goes outside, there is a problem. This makes it easier to see the change without getting stuck on a single number. A small habit before measuring makes a big difference. Quickly wipe the contact tip and the measured surface. Avoid holding the part for a long time and warming it up, and do not press harder than necessary during measurement. These small details can strongly affect the outcome when working with tight limits. So how do we quickly check? Is the tool correct? In everyday work? We are not doing a laboratory procedure. We are doing practical verification. On a suitable stand, check 2 or 3 points across the range using a few different gauge blocks. Approach the same value from the same direction every time. If the reading changes each time you return to the same block, this is very often setup related, mounting, angle, dirt, or contact. If the setup is solid and it is still inconsistent, friction or backlash inside the indicator is also a possibility. In summary, an indicator is for reading deviation. For reliable results, focus on 3 things: a solid setup, the correct contact direction, and a consistent approach direction. If these are right, both dial and digital types can do the job. To follow the measurement equipment series, don't forget to subscribe to the channel, like the video, and leave a comment.